to the second category of symmetric ciphers, which is substitution ciphers. Now, in this category, each letter is uniquely replaced by another letter, and that is why it is called substitution. You have to substitute a letter with something else, with some other letter. Okay, now here please remember, you have to substitute a letter with another letter. Okay, this is the substitution cipher. Now, if I will ask how many possible substitution ciphers you can get from the English alphabet, from A to Z, how many different or how many unique possible substitutions are possible? Each letter is uniquely replaced by another. Okay, so definitely if it is uniquely replaced by another, in decryption what you need to do, you need to again resubstitute the letter, the original letter, right? And for that you need some mapping sort of a thing. For example, like this, maybe A is replaced by N, and then N will get replaced by A again, something like that. Okay, some sort of mapping will be there. So how many such mappings could be possible? If we talk about English language, how many mappings could be possible? So, for example, how many characters with which A can be replaced? There could be 26 possible characters, because A could be replaced by itself. It is also one possibility, right? Identity mapping sort of a thing, right? So there are 26 possibilities in which A can be replaced with. Now, B can be replaced by 25 possible categories, because one we have already used to substitute letter A, right? Similarly, when we talk about C, there are 24 possibilities, and if you come up with the all possible combinations, then it will become nothing but 26 factorial, and this is how it is. It is been calculated. So there are 26 factorial possible mappings in which substitution can be done in English language, right? And specifically, we are talking about everything in capital letter, to be very much specific. If we take small letters into consideration, you can calculate accordingly, right? So there are 26 factorial possible substitutions. You can pick any particular substitution cipher, and then you can go ahead with that, right? But both the parties should agree on the same mapping or the same substitution method or map, right? So there is one quite very famous substitution cipher which is used in internet post, that is ROT13. Okay, the full form is something like rotation 13. You have to rotate the entire thing by 13, right? So it was considered that since there are 26 letters in the alphabet, okay, so in our English alphabet, so there are 26 actually alphabets. So just divide it into two groups, 13 and 13. So these are first 13 alphabets and next 13 alphabets. And the map is quite simple. You just have to map it like this. Okay. So A is replaced by N, B is replaced by O, N is replaced by A, O is replaced by B. Things like that, right? So entire alphabets are divided into two groups. Okay. And if we are following this method, ROT13 method, then if we have to convert hello, the ciphertext will become URYYB. Okay, B is this, yeah. Okay, similarly, you can come up with hello world, world also. So you can find the mapping of world as well. And now this will become our ciphertext through ROT13 method. Okay, similarly, when you have to decrypt it, you have to just reverse the process. But you have to be in the possession of the same mapping. Okay, now if I will ask you, what is the key here?
Plus 13.
Plus 13, right? Or 13 is the key. In encryption, you have to do plus 13. Maybe in decryption, you have to do minus 13. Or maybe you have to do left rotate and right rotate, something like that. Okay, by 13. So 13 will become the key, and this is the same key shared between encryption and decryption algorithm, or sender and the receiver end. And this is the plain text. This is the cipher text, and the algorithm is, you can call it as rotation. Okay, you have to rotate it with some k. So this will become our algorithm. Yes. Now let's discuss a specific, a very quite a popular, cipher, which is a substitution cipher, Caesar cipher. Okay, it is given by Julius Caesar, and what he said is quite simple. So he said that, okay, this, if this is the plain text, what you need to do, change each letter to the third letter of the following, which follows it, right? So if you have to replace A, you will just see in this series, and you just go to the third letter. So leave B, leave C, and pick D. So A is replaced by or substituted by D. Okay. Similarly, B will get substituted by E, so on and so forth. Okay. So change each letter to the third letter following it. This is the Caesar cipher. Okay. What is the key here? Key is 3, and the key is usually written as D. Okay, and some of you is asking that whether the key is numeric. Underlying thing is it is numeric. You have to somehow mathematically calculate it, but yes, you can represent it in the form of alphabets also, right? So here D, because A is will get replaced by D, and the the method will be followed, you know, for the remaining letters, right? So if you want to change plain text hello world, the cipher text could be, will be, if you apply Caesar cipher, the cipher text will be this. Okay. H, you have to leave, I, J, and you have to put K. E, you have to leave F, I mean, what will be there? A, B, C, D, E, F, G, H, I, J, right? So after E, E should be replaced by H, things like that. Okay, and this could be followed. So this is Caesar cipher. If we have to see the crypto system, definitely what is M? It is a sequence of letters. What is K? Now here comes your point. K is a set of integers. Since we are talking about the English language, this is, between, the key will be between 0 to 25, because the rotation is done in that manner, right? What is the Caesar algorithm? In the message, you have to add some key, and then you are taking mod. Why mod? What is the need of taking the mod? Because suppose if you are uh, replacing the letter Z, okay, so what you have to do is, Z is 25, so you have to add key, that is 3 in 25, and then it will become 28. So for this you have to take mod, right? So mod 26, this will give you 2. Okay, so A, B, C, 0, 1, 2. So you have to replace Z by C. Okay, so this is the encryption algorithm, and reverse of this is a decryption algorithm. Okay, and what is C? C is again a sequence of letters, right? So this is Caesar cipher. If we talk about the attack particularly, one possible attack could be brute force attack, right? Exhaustive search. How many keys are there? How many possible keys? In Caesar cipher, how many possible keys? 36 possible keys are there, right? So one possibility could be you can do exhaustive search, or exhaustively you can, try each and everything, which is nothing but a brute force attack. Second thing could be doing some statistical analysis. Okay. So as a homework, I'm giving you that you have to think how statistical analysis is used to break Caesar cipher. Okay. Plain text is known to you. Cipher text is known to you. I mean, you can just consider this cipher text. You know that this is a Caesar cipher which is used. Okay. Uh, Definitely key is not known to you. Then how you can use statistical analysis to come up with the plain text message. Okay. Statistical analysis, what we are trying to achieve is somehow we are trying to exploit the given knowledge which we have about the ciphertext, right? So you know that this is the ciphertext. You know that its corresponding plain text is written in English. Okay, so these are the two things, and you know that this is encrypted using Caesar cipher. Using all this knowledge, can we do a little bit better than exhaustive search? Okay, this was the idea. So actually, yes, the answer is we can do better than this using frequency analysis. Okay, so let me tell you that any natural language, not only English, but any natural language you can pick, it is not uniformly distributed, right? Each letter occurrence varies from the occurrence of different letter. Okay? So if we talk about English language, this could be a possible frequency and a frequency table with respect to each alphabets which are present in English language. Okay, and this is well known, right? You know, if you do a Wikipedia search, you can get a table like this, a frequency table like this. Okay, so the knowledge of letter frequencies, not only letter frequencies, but we have the knowledge of, you know, pair frequencies, triplets frequencies, quad frequencies, twin frequencies. So we have, you know, such knowledge, and we actually trying to use all this knowledge while conducting our cryptological attack against any substitution ciphertext, right? So what we are actually concerned right now is Caesar cipher. So let's see how we can actually crack Caesar cipher. Okay, now it is a little bit evolved, so you have to pay attention. Get started. Okay, so first we have to understand what do we have. Okay, what do we have? What do we have? We have the ciphertext. Okay, this is the ciphertext corresponding to hello world. Okay, we are not aware of what is the plain text. Okay, we know that this is a ciphertext uh, which is actually encrypted using Caesar cipher. Okay, so these two things we are aware of. What is our goal? Our goal is to find the corresponding plain text with respect to this ciphertext and the possible key. In Caesar cipher, uh, these two things are trivially derived from one another. If you know plain text, you can derive the key. If you know key, you can easily derive the plain text, right? So this is our goal as a cryptanalyst. Okay, let's see what we can do. So let me take you through the entire algorithm. Now you have to observe one very beautiful thing in Caesar cipher, and that is, let me write the plain text. So this is the plain text, hello world. Okay, and this is the corresponding ciphertext. When we talk about Caesar cipher, one thing is quite clear, that there is a very high frequency correlation between the ciphertext and the plain text. Meaning, if K comes, once in the entire text, okay, the letter corresponding to this K in English also appears only once in the original text. Here, suppose O is coming 3 times in the entire text. Whatever letter which corresponds to O, okay, so O is a ciphertext character. Whatever character which corresponds to O in the plain text also appear 3 times in the entire text. Okay, so this is something which is called frequency correlation. There is very high frequency correlation between the ciphertext and the plain text. Okay, and as a cryptanalyst, we are actually trying to exploit this particular characteristics of plain text and ciphertext, right? Or we are actually would like to exploit this particular knowledge which is available to us. Okay, and with this knowledge, actually, we can try to reduce the number of possible outcomes. Okay, so let's see what we can do. As a first step, what we have to compute it, we have to somehow compute the frequency of each letter in the ciphertext. Okay, with this, we actually get to know how many different characters are present in our plain text. Okay, so can you tell me how many different characters we have in our ciphertext? One is K, then H, O, R, Z, U, and G. That's it. So there are these 7 distinct characters present in the entire ciphertext, right? And similarly, we get one more information about the plain text, that in plain text also there are these 7 different character scripts, right? All right. Now, there if we know that how many distinct characters present in our ciphertext, we actually get to know how many distinct characters are present in our plain text as well. Okay, so our job is to compute the frequency of each letter present in the ciphertext, right? So total letters in the ciphertext are 10. Okay, there are total 10 characters. What is the frequency of K? Frequency of K is 1 by 10. K appears only once, so frequency of K is 0.1. Frequency of H again is 0.1. Frequency of O is 3 by 10. It appears 3 times, so 0.3 is the frequency. G 0.1, U Z 0.1, and R is having 0.2 frequency, right? R appears twice in the ciphertext. So this is what we have calculated. Somehow we have calculated f of C, where f represents a frequency of the character C in the ciphertext. Okay, this is our first step. Now, the second thing which is known to us is this character frequency. As I already told you, this is something which is quite known to everyone. Okay, whenever you do a Google search, you will find the frequency, character frequency with respect to each and every language. If not, you can even derive it by yourself also. Okay, so this is the character frequency which is available to us. Now, what we have to do is we have to establish a correlation between the frequency of letters in the ciphertext and the frequency of alphabets in English. Okay, this is what we are trying to establish. Okay, let's see what is the exact method. So f of C we have already find for each character. We got the frequency of character in the ciphertext. Now we have to find out phi I. Now what is phi I? Phi I is a correlation between frequency of characters present in the ciphertext with the with its corresponding letter, frequency of its corresponding letter in the English. Okay, let me call it as Z, suppose. Okay, so for example, if I am writing L, L is a letter of plain text, and its corresponding ciphertext is O. Right? So what phi I is telling me? Phi I is telling me the frequency of letter O in ciphertext, correlation between frequency of letter O in ciphertext with the frequency of letter L in English. Assuming that I is the key. You have to assume that your key that you are using is I. Are you getting my point? Okay, so you have to somehow calculate this correlation, value of the correlation between these frequencies. Okay, for that matter, let me derive the exact formula for you. So, so C may varies from 0 to 25 because there are in all 26 characters in English alphabet, right? We already know that we are talking about English, and it can be generalized with respect to each and every language. Okay, the method will be same, only the ranges will change, right? So what is this correlation? How can we establish this correlation? So this correlation is actually the sum of frequency of letters in ciphertext with corresponding frequencies of a letter in English text, assuming I as the key, right? So let me again take the same example of the ciphertext that we are dealing with. So the ciphertext we are dealing with is this. I think ZR. Uh, what is it? CUG? UOG, I think. Yeah. Okay. This is the ciphertext we are dealing with, right? Now, how we can calculate the correlation frequency? So we will say, okay. So we have to first take f of c, okay, f of k in this case. So first letter is k. Let's talk about k, f of k. Now, let me again write this A, B, C, D for you. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W. Okay, so you can go till Z. Now, what I have to do is this. So first of all, what is f of k? F of k we already find in the previous slide. It is 0.1. Okay. So this is the value of f of k. We have to multiply this with, now what will be the, if suppose I is the key, which letter corresponds to k if I is the key in plain text? Yes. In Caesar cipher, we took the message and we add key into it. Okay, and then we will take mod or something like that. Right. So the main formula is you are actually adding the key in the plain text. Now here actually what we are trying to do is we are trying to decipher the things. Okay. So if the ciphertext letter is K and the key is I, what could be its corresponding English alphabet? It could be, so what is K actually? So K is here. K is actually 10. Okay, so if you count from 0, this is the 10th position. Okay, so 10 minus I will give you corresponding English letter. Are you, let me explain again. What is phi I? Phi I is a correlation function. Okay, it is a correlation function. Assuming that I is the key. Let's assume that there is a key I where I varies from 0 to 25 definitely. इन्हीं में से कोई एक की होगी, इन्हीं में से किसी एक नंबर से शिफ्टिंग हुई होगी, right? In exhaustive search, what we are doing, we are taking all possible combinations of 5 and we are actually applying it on the ciphertext. Okay. Now here what we are doing is we are not applying anything. We are just calculating which particular value, which particular value of I will establish a strong correlation between the ciphertext and the plain text. This is the overall idea. Okay. For that, what we will do is we will take each character of ciphertext. So first, let's start with K. So what we have to do is correlation is a product of frequency of the letter in the ciphertext with its corresponding English letter, with the frequency of its corresponding English letter. So frequency of K, we already know, we have calculated it in the previous slide. Frequency of K is 0.1. Now what is the value of P? I mean, what is the character which corresponds to this K? So we will say that if we assume that I is the key, what you have to do, you have to shift, K times in the left direction. Okay. So you have to actually minus I from K. What is K? K is 10. If you minus I from 10, then you will actually get the corresponding letter of K in English. Okay. And same goes with each and every character. So in this, we will add, what we will add? We will add the same correlation for H. Okay, so frequency of H in the plain text multiply by frequency of which character you have to see in English. So in English, if so H comes here. So what is this? 4, 5, 6, 7. This is 7, 7th position. You have to shift I times in the left direction or in the upward direction. So it becomes 7 minus I. This is the character which is corresponding to H. This is the character in plain text which corresponds to H in ciphertext. Are you with me here, everyone? Yes, please, you need to understand this underlying math. Yes or no?
Yes, ma'am.
All right. So this is what we did in the entire thing, right? So we have actually 7 distinct characters. Okay. So we get 7 distinct terms here. And we applied the same thing that I have just explained. You just take the letter. So for example, O, the frequency is 0.3. Okay. So 0.3 times O will come here. So this is the 14th position, 14 minus I. Okay, that is the character which corresponds to O in plain text. Okay, so we will have this formula. Now our next job is to compute this correlation value for all possible values of I. We have to compute the value of correlation for all possible values of I. Okay, what you need to do, you just assume that I is 0, compute this entire value. Okay, how can you do that? So suppose I is 0, it means P becomes 6. What is 6? 6 is nothing but, I think, G. Okay, so what is the probability of G? I mean, what is the frequency of G? So you just take frequency of G here and you have to multiply it. Okay, so you have to do the same thing for all the 26 possible values of I. And this is the table you will get. This is the table which shows the correlation value for all possible values of I for the given ciphertext. Okay, so again, we are considering the same ciphertext. Ciphertext we are taking into consideration, and with respect to this ciphertext, these are the values of correlations. Okay, just keep I 0, then 1, then 2, so on and so forth till 25. Okay, so this is the correlation value. Now what? Now what you have to do is you have to find the strongest possible correlation. Now what is the strongest correlation? What is the value of I there? Case is 6. The most probable possibility of I could be 6. Okay, because here we get the highest value. Now as a second step, what we will do is we will assume that our I is 6 because it is having the highest value. And now we will try to convert our ciphertext as per this particular key, assuming that this is a key. Okay, so when you convert the given ciphertext, assuming 6 as a key, you will get this as a plain text. Okay, now you can identify, okay, that this may be, this is not making much sense. So what you will do, you will go for the next possible correlation, right? And it is, if you see, it is 10. Okay, so this is 0.676 and this is 0.631. So you will assume after that the value of I could be 10, and then you can derive the plain text, from the given ciphertext, assuming the key is 10. You will get this as output. If you see that, okay, this is also not a very meaningful thing to have with, you can go for next probable value. Okay, and the next probable value is 14. The probability is 0.0561. You will get this ciphertext. It is also not looks very, very familiar or meaningful. You can go for next possible value, which is 3. Okay, or maybe I think there is something wrong. I think 14 is having lesser value than this, I guess. So maybe at the third position, you will try 3. And actually, it will give you the right answer. Okay, by just reading the sentence, you can get to know that yes, this is the plain text we are looking for, or this could be a possible plain text corresponding to the given ciphertext. Okay, so when we are doing exhaustive search, we have to, convert the entire ciphertext 26 times. Okay, whereas in this case, only in few trials you can get to the exact plain text which is corresponding to the ciphertext. Okay, so in this way, using the statistical knowledge, we are actually optimizing our cryptanalysis algorithm. The worst case, you need 26 trials or 26 such iterations. That is true. Okay. In the best case, whatever is the highest, probable value or highest correlation value, you will get it right. That will be the key. On an average, you have to do 13 iterations on an average. Okay, so in these cases, we actually, so when we are doing statistical analysis, we are just trying to do better than our existing method. So in our existing method, for sure you have to explore 26 cases. Okay, but in this case, what you have to do is you can design an algorithm which can stop in between after few iterations.
Okay,
Complexity
ma'am.
also, if you see the complexity also, even in the worst case, this particular algorithm. So let's talk about a case where you are using, the normal method. I mean the brute force search. Okay, and let's assume our same example that we are having 200 words in a document, and on an average, say each word consists of 4 letters. Okay, so approximately there are 800 letters, 800 different letters in your document. Okay, if you go by exhaustive search, how many conversions you have to do? You have to do 800 letters should be converted 26 times. Agreed? When you deal with statistical analysis, what we are doing is we are actually doing this calculation only for distinct letters. And how many distinct letters could be possible in English? There are only 26 distinct letters. Okay, so at max, how many times you have to compute this phi? 26 into 26 times. Okay, and then you just have to sort your correlation value and work accordingly. So in case of brute force, the complexity is 800 into 26, which is reduced to 26 by 26 approximately. Obviously you have to add some more thing, but it is in the addition. This is the highest time, this is the highest time consuming process. That's it. So Caesar cipher is not considered to be a strong cipher because the problem lies in the key. The key is very short. It is just one letter. Okay. And if somebody will find that key, we are done. Okay. The key could be found by exhaustive search in the worst case. Okay. If you apply statistical frequencies, it is also not concealed well, right? Because there is a very strong correlation between the frequency of English letter in plain text and the ciphertext letters. Right? There is very strong correlation. So statistical frequency is also not concealed well, right? So the idea is somehow if you want to make it stronger, you have to make the key longer. Okay, it should not be a one letter key sort of thing, right? So then, people come up with other cipher algorithms, which is based on multiple letters. Let's put multiple letters in the key instead of a single letter. Okay. And the overall idea is somehow to make this statistical frequency curve more smoother. Okay. So that it can cover more number of samples. It just to make the cryptanalysis a little harder. They have to work, a lot more to break the given algorithm.